So, probably you already talked about the general shape of sensitivities. Now, I would like to show you some applications. For example, sensitivities taking as control variables the real power, which is one of the most used, because you use this kind of sensitivities for the dispatching, for example, for security constrained OPF, another application. In this case, okay, this is the Jacobian, and it's always the same. It's the well-known Newton Jacobian. This is the matrix of the derivatives of the power flow equations with respect to U. But now U, what is U now? U is the vector of the real power injections, that is this P, this and this. In particular, if I consider only the real part, it's only P, this one. So what is the derivative of these equations, these functions with respect to P? It's 1, because it's P minus something. So the derivative with respect to P is 1. In other words, this matrix is simply the identity matrix. Okay? So if I want to compute, for example, the derivatives of deltas with respect to P, this is just okay, this is the inverted matrix, but it's a part of a submatrix of the inverted Jacobian times the identity matrix, so it's times 1. So in this case, it's very simple. You can also use these concepts for voltage rescheduling. What is voltage rescheduling? It means that if you want to solve some problems, typically some reactive problems, by changing the values of voltages at the generator buses, so you have a problem in the network, you want to check if it's possible to solve this problem, for example, by increasing the voltage at a specific bus of your network. You can compute the sensitivities of your state variables with respect to the voltages at the generator buses. So in this case, this matrix will hold the derivatives of these functions with respect to Vg, and Vg is a subset of these voltages. So you have to write the power flow equations and to find out the correct derivatives, and you will put it in this matrix. You perform this product and you will have your sensitivities. So it's a very powerful tool to set up optimization problems, security problems. A lot of problems are solved. I could say probably all the power system problems in some way make use of sensitivities. This is a further case. Maybe this is more difficult because in this case it's more non-linear. You can, for example, use as vector delta U the admittances of branches. So you compute, in other words, how voltages and angles change if you change the admittance of a line. Why can this be useful for you? Because if you have your large power system and you want to remove one branch, this is the so-called n-1 security analysis, it's a linearization. It doesn't work because it's a large perturbation. This is a large perturbation. You lose an electrical line. But it can give you an idea. So removing a line means that you move from the admittance of that line to 0, right? So you apply a delta y, which is exactly the admittance y of that line, and you find out how voltages and angles change. You can also find out how currents at that point will change. It's not an exact computation. If you want to carry out an exact computation, you must solve a power flow case. But it gives you an idea. So you can, for example, identify what are the worst, the most dangerous contingencies. And it can work. So these are, there are lots of applications. And we can apply to our problem. So we can compute, this is the linearization of this system. We can find out the angles if the power changes at bus number 3. So these are the changes in the angles, and we can compute the sensitivities. So this is the sensitivities of how the power flowing from bus 3 to bus 1, this one, changes if you have an injection of 1 at bus number 3. So if you look here, this is the power from 3 to 1 and from 3 to 2. So you see that if you add an injection 1 here, you will have 0.66 going to the slack bus and 0.33 going to that bus. And if you look at the congested branch, which is 2 to 1, you see that if you inject 1, you relieve the congestion by 0.33. That's why to relieve a congestion by 30 megawatt, you need to inject a 95 megawatt here. So that's exactly the picture of what we obtained before. So you can see in this case linearity is very effective, because this problem is very linear and this approach is very fast, not always using voltages. So using voltages now, this is the problem. If you want to move to change the value of voltage at bus S, generic bus S, you will have some buses J where you can change the voltage, typically generators. So you have a set of generators. You can move their voltages. You can change the set point of the automatic voltage regulators. And these are the sensitivities. So you know that changing these voltages, you will obtain a change in voltage at bus S. But also you can move some reactive power injections, for example, by switching on or off capacitors or reactors, or changing some reactive loads, for example. And you can compute the influence on voltage at bus S in this way by using sensitivities. Take into account that usually you have to be careful, because let's assume ES is low. So you want to compute control actions in order to increase ES. You compute some control actions, but you also must check that the situation will be good for other buses. So if you have any other bus, this voltage will must not be negatively affected by the control changes, the control actions you are carrying out. Okay? So typically you have to control a few voltages, and you have a lot of control variables to move. So this is not a system of equations. This is you have less equations than control variables. So this is a typical case when you want to optimize your system. So you will select an objective function, and you will have some constraints. Among the constraints, you can put that voltages are between, for example, 0.9 and 1.1, the rated value. optimize means minimizing losses or any other objective function you may have. So now let's have a quick overview of what are the possible control actions, starting from the strangest control actions and moving to the most traditional ways to control voltages. The first one is the insertion of an electromagnetic force, delta E, in series. So you imagine now exactly what you told me before. Imagine you have a line, and so you have an electric line, and this is your big system. You cut the line here. So this is bus P before you open this line, and here you insert this delta E. So you split this bus into P prime and P second. Okay. Typically, this is not made in the middle of the line. It's made here or here, but the concept is the same. So what is the result of this ideal change to my power system? Okay, let's assume that my system is essentially inductive, has inductive characteristics here. So if I insert this delta E, the current will be lagging 90 degrees with respect to delta E, right? So this is equivalent to injecting a reactive power into bus P second and withdrawing reactive power from bus P prime, okay? So I can study the system in this way. So this is my voltage EP before the insertion of this series electromagnetic force, delta E, which is assumed to be in phase now with EP. And these are the two currents injected in. So I have Q second, EP second, delta I into P second. And I'm taking reactive, it's not the same, reactive power, EP prime, delta I from bus P prime. At this point, I can use a sensitivity analysis because I compute how, for example, voltages will change in my system given this change in reactive power injection. So I will compute the derivatives. I can use this kind of derivatives. How ES changes if I change the reactive power at that bus. Okay? So this is how. So we can see how what we can control if we inject an electromagnetic force in series into the line and in phase with the existing with the previous voltage at that bus. Okay, these are three ways to control the system, but this is the new value of a generic voltage at bus I. So this sensitivity, I need this sensitivity and this sensitivity. Okay? I can also use a different approach, so I will insert my delta E, but now I assume that delta E is not in phase with the voltage at bus P, but it's leading or lagging 90 degrees. Okay? So the concept now is that, let's assume EP is 400 kV. The value of delta E will be some kilovolts, not more than that. So delta E is much lower than EP second or EP prime. So this triangle is very, very narrow and high. And in general, I can assume that this angle is, the sine of this angle is, can be approximated by the angle itself in radians. So this is the relationship I can obtain. And I can see that in this case, I can control the angles. So you know that, so if I insert the voltage in phase with the voltage before the insertion, I can control reactive powers, and I will be able to control voltage magnitudes on the network. In this case, instead, I can control the angles delta, and probably I will be able to control real power flows, which are associated with the angles. Okay? So two different goals. Okay, so this is the resume of that. Other devices to control voltages, shunt devices. This is the most traditional way to control voltages, synchronous machines. I will talk about that later. On-load tap changers also, reactive compensation. We talk about that. Synchronous compensators. Do you know what are synchronous compensators? Synchronous compensator was one of the oldest tools to control voltages when I was a student. I saw the last synchronous compensator in Milan in 1983 or 4. It was the last one. But today they are still they are very cool in the sense that new problems are present in power systems, and these problems are due to renewables, short circuit power, inertia of the system, so that, for example, in Italy they are installing a lot of synchronous compensators just in these years. So we have cycles on the history. Do you know what synchronous compensators are? Okay, you know it. They can be managed just like normal synchronous machines. Then we have mechanically switched capacitors and reactors, and this is just what I depicted here before. Then we have some devices coming from the power electronics. SVC, the general set of static VAR compensators that include these different types of devices. I will show you a quick view later. And this is let's say, this one is the big family of FETs, flexible alternate AC transmission system, that are devices based on power electronics, able to control both the reactive power and voltages, and in some cases also the real power flows, and also booster transformers. Let's have a very quick look. These are TSC, that is, what is T? I can't remember. Thyristor. Switched capacitors, okay, by means of these switches given by the power electronics. Thyristor control reactors, okay, filters, and an automatic voltage regulator. So this regulator can, in this case, switch on and off these capacitors and can control the overall reactive power injected at this bus by moving in a continuous way the reactive power withdrawn by these reactants. Are you familiar with these devices? Yes. Okay. So this is the first way. This is the STATCOM. Here we assume the voltage is kept constant by this capacitor, and this device can provide a voltage VA. If VA is higher than the voltage at that point, it will inject reactive power. If this is lower, it will withdraw reactive power from the grid. So this is another controllable device, okay, with some advantages and disadvantages with respect to the other devices. And then there are some other devices for the series compensation. So thyristor control series reactors and thyristor switched series reactors based on the control of this tool. And here we have the same with the capacitor here. So you can, in this case, compensate the line. Again, we have thyristor control switched capacitor or thyristor control series capacitor and thyristor control switched series capacitor. Okay, they are the same family, and these are more complex FECS devices. This is the UPFC, Universal Power Flow Controller, which has two transformers, one shunt transformer which provides power to a series transformer injected on the line leaving the same bus. So you can take power in a form and inject it again in the other form. All these devices are very flexible. The problem is that they are very expensive also. So as far as I know, in Italy we don't have any one of these devices. Let's say that these typically, no, we have these devices especially close to very polluting from the electrical point of view users. For example, steel factories may make use of these devices, but not for the control of the power flows, because there are many ways cheaper to do it. Okay. So now let's look at the general problem of the voltage control. And this is related also to limits of generators. We have always the same formula. We have the voltage at the user or terminals. What if we are able to control this voltage? Usually, if we have a generator, we have also an automatic voltage regulator able to keep this voltage constant. Okay, if this is true, I can write this formula and I can say that delta VU is more or less, neglecting all resistances, dependent on this equivalent reactance, where the equivalent reactance includes the sum of XL plus the reactance of the transformer. Okay? So this means that if this number is big, the voltage here will be affected by the change in the reactive power withdrawn by the load. What happens if let me check. No, okay. What happens if my generator is no longer able to control this voltage? For example, because it reached its capability, so he lost the control of the voltage. This means that I must add to this equivalent reactance the internal reactance of the generator, the synchronous reactance, which is large typically. So I will increase the value of XE, and this means that with the same perturbation delta QU, my system will show a higher change in delta VU. So in other words, the system is weaker, and it's reasonable. I lost the control of the generator, the system will be weaker. On the other side, let's assume I have the full control of this voltage, and I can also control this voltage. This happens. You may have a very large power plant, and in some cases you are able to control the voltage at the high voltage bus bar of the power plant, the 400 kV bus bar. So in this case, which is the opposite of the previous case, XE is only equal to XL, so it's very small. This means that the voltage VU will be less affected by any change in the reactive power. Okay? So the ideal case is to try to control the voltage as close as possible to the load, if we are able to do it. In general, we must face the problem of the capability limits of the generator. So we must be careful. We don't want to lose the control. In general, the system is in good conditions if the voltage is high, but not always. And in general, if the reactive load increases, then you must increase the excitation current in our generator. This is the normal operating conditions. But in some cases, when the system is not very loaded or close to the no load conditions, for example during the night, or just after a blackout, this is a big problem during the restoration of a system after a blackout, but hopefully this is not a common condition. But in general, during the night, you have the opposite problem. You have an excess of reactive power into the grid, which raises voltages, and so your generator must absorb this reactive power, so they must be under-excited. So you see that the problem of the voltage control is very different depending on different operating conditions. So at this point we must look into the power plants and see how the voltage control is carried out by generators. So the excitation system of a generator has the goal of keeping constant the voltage depending on different operating conditions, that is, as the load changes, where the simplest case is at the generator terminals. So you have a controller, measures the voltage at the terminals and moves the excitation current accordingly. But you can also do it at the HV bus bars of the power plant, for example on the 400 kV level, or you can control the voltage at a different bus. For example, in this case, you could measure this voltage and move the excitation of this generator in order to keep this voltage constant. This is the first step towards what we have partially in Italy, which is the secondary voltage control. But this can also carried out by a particular control which is called the compound control of the excitation system. So keeping the voltage constant is very easy to understand, but also there are some other goals of the excitation system of a generator. To control reactive power sharing among generators. If you have 4 generators in the same power plants, you don't want that the first one will produce 100 megawatt, and the second one 20, the third one 0, and the fourth one minus 40, because that would be crazy. So you want possibly to share among the 4 generators, depending typically on their rating, and if they are equal, the same amount of reactive power. To control the fulfillment of the capability chart, the chart that gives you the limits, the operational limits of your generator, to contribute to the power voltage security. So looking from a system perspective, you want to move, to reschedule the voltages of your generator in order to avoid the voltage collapse, in other words. During transient, when you have a short circuit, you want to increase to reach the so-called ceiling voltage, the maximum voltage, in order to preserve the angle stability of the generator. Avoid over voltages in case of load disconnection. Okay, some other. This is important. Improve the damping of electromechanical oscillations. So you see that the excitation control is very complex and has a lot of different goals. Let's. I was looking at this PC. I was not. Okay. For example, stability. I think you saw something about stability. What happens if you have a short circuit very close to your generator? The first issue is that this generator will increase the speed, right? Because the transmitted power will be equal to 0, while the power coming from the turbine will be kept constant, so the rotor will accelerate, right? And the rotor will accelerate, and at a certain point, the breaker, the protection system, will trip the line, and the fault will be removed from the system. Okay, so at this point, you see you will have some oscillations, and then the stability is in this case is safe. Okay, but if you wait too much in tripping the fault here, okay, in this case you see a different shape that makes you suspect that this situation is worse than the previous case, but okay, you are safe. So in this case, the fault clearing was at 0.34 seconds. If you use 0.35, you see that it's too late. In this case, your generator is not stable, and you lose stability. You will lose this generator. Then you don't know what happens to the system, but for sure that generator will be disconnected. Okay? So in this case, the excitation system of your generator must, if possible, of course, the best solution is to decrease the clearing time. But another option is to force the voltage, if you can, force the voltage to higher values, to the so-called ceiling voltage, that is to increase very quickly the voltage, the excitation voltage, because in that case maybe also with 0.35 seconds the stability will be preserved. You can try. This is one of the options. Another issue of excitation system is the damping of electromechanical oscillations. You can see that this is a disturbance in 2006, and this is the voltage, the European voltage. I can't remember where. Okay, in Greece. The blue one was in Greece, and you see that while the red one is more or less stable, the blue shows some oscillations, 0.27 Hertz, which corresponds to one of the eigen values of the system. Now, I don't want to go into the detail of small disturbation, small perturbance angle stability, because this is a typical problem. But this is just to say that one of the signal used to control the voltage in the excitation system of generators has the goal of damping this kind of oscillations. So the excitation system also has to manage this kind of problem. So not only voltage problems, not only over-exciting or under-exciting in order to increase or decrease the reactive power injected. Also stability, also small perturbation angle stability. This is another type of the same problem you see the time. Okay, the time is here. These are not 50 Hertz. These are maybe 1 second, 2 seconds, something like this. So you may have these oscillations which are of the same time of the same kind of this one, but you see what happens here. That one was a blackout in California in '96, and that one was the simulation. So they were not able to reproduce the real. This is the real occurrence. This is the simulated. The simulated was very secure, and they had 2 blackouts in 20 days, something like that, due to the same reasons. Oops. So I will skip all these subjects but if you want to have a look, it's not prohibited. So the automatic voltage regulators has a lot of goals, not only the simplest one. This is again, okay. Practical cases. I mentioned what to do in case of small perturbation angle stability. I mentioned that you may have an additional signal. This additional signal was represented here. Okay, just for you to know what is the meaning of this. PSS means power system stabilizer. This is an additional signal that can be injected into the excitation system. So this is the excitation, the controller. For example, they are not. The measurement of the voltage is not represented here. Here. Okay. So you can imagine. This is the dynamic model, the second order model of the generator. Do you know it? Yes. Okay. The overall one is the fourth order model, and this is the excitation system. So you can see that here I have the signal related to the voltage measurement. So I can increase or decrease my excitation current depending on the value of the voltage at the terminals of the generator. Okay. But I have an additional signal here, which is a signal that is different from 0 when you have a situation like this one. You have oscillations increasing or not damping properly. Okay? And you can see the red one is the case when you don't have this additional signal. The blue one is the case with the PSS. So the PSS has the goal of damping low frequency oscillations, and it's one of the signals provided by the excitation system. Other cases, the ceiling voltage. I already mentioned what is the ceiling voltage. When you have a short circuit, you try to increase suddenly the excitation voltage in order to reduce the probability of losing the step of your generator. But you may also need a negative ceiling. When do you need negative ceiling? When you have a load disconnection. In that case, you want to force to zero, in italiano si dice diseccitare, to reduce to zero the excitation current in the fastest way you can. And you can do it if you are able to change the sign of the excitation voltage, because if you don't change the sign, you will have an exponential decrease of the excitation current. If you are able to change the sign, you can go faster to 0. And this is the case of the disconnection of a load. This is, for example, a problem when you have permanent magnet generators, because you cannot control the flux with this excitation system. So in that case, when you have a load disconnection, you will see the voltage at the terminals of the generator going to 2 or 3 times the rated voltage, which is a problem. Okay, so that was animated by the PDF, doesn't work. So here you have the different components of the excitation system. You have the regulator here, and this is the voltage. These are some additional signals, the PSS, as I mentioned, but also the compound and droop. I will talk maybe I have 5 minutes left. Limitation and protection. I don't want to exceed the capability of my generator. Let's talk about first the capability. I think you are familiar with this. But one of the duties of my excitation system is to check that you are always within the capability chart. And you know that the capability chart depends on voltages, so it's not so easy to manage as you find in the books, because this limit depends on voltage and changes in this direction as voltage increases. This limit depends on voltage and change on the opposite direction as voltage. So it's not so simple as you can find in the books, but okay, you can manage. I would like to talk about compound, which maybe is less known subject. What is the compound? The compound is another type of reactive compensation. You have a generator. It's not here. You have a generator. You have a load, and you can say, okay, as the load increases, as this load increases, if I keep the voltage here constant, I know that I will have a given voltage drop here. Okay. But I can say, okay, if the Q increases, the Q of the load increases, I will increase also my VG in such a way that, okay, probably the voltage VU will decrease, but less than in the previous case. This is the concept of the compound control. It's a kind of compensation. When this increases, you also increase the set point of your AVR. Okay? Unfortunately, it's not so easy to use it, because, okay, let's say we have this characteristic, and this is the compound characteristic. So when the slope is positive, we can say this is a compounded regulator, while this is a characteristic with a droop, which is exactly the same concept as the droop in the frequency control. So, for example, the idea is why compound? Because if when this loading increases, I increase the set point of voltage here, I can see this phenomenon like this one. It's like I take the measurement here and try to keep the voltage in this point constant. It's exactly the same thing. So this is the transformer. This is the synchronous reactance of generator. If I adopt a characteristic with a compound means compensation. What I'm going to compensate? I'm going to compensate this part, the red part of the reactance of the transformer. So I can see like the case when I measure the voltage here and keep try to keep the voltage here constant. This is the meaning, the physical meaning of the compound. But you need to be careful. For example, let's assume you don't have any compound. This is one of the possible schemes to connect two generators at the same bus bar. Then you have the transformer here. Okay. If you measure the voltage here and control the excitation system of each generator, this can be a dangerous situation. Why? Because let's assume the measurement of G1 is a bit wrong, has an error, it's normal, while the second one is perfect, not so normal, but we can assume it. So let's assume here you must keep 10 kilovolts, but that meter, the meter of G1, measures 9.99 kilovolts. Okay? So G1 will try to increase its reactive power. And increasing the reactive power, the voltage here, which is 10 actually, will go to 10.01. So that the meter of the second generator, we say, oh, the voltage is raising, so I have to inject less reactive power. And in this way, the voltage goes down. So the first generator say, oh, the voltage is still going down. I have to increase my reactive power. So in the end, you will have a flow of reactive power going from G1 to G2. It's a very ineffective way, of course, but in the end, one of the two will reach its capability limit. The first one in over-excitation, the second one in under-excitation. One of the two will reach this limit. Okay? So, compound 0, let's say that the flat characteristic with this scheme cannot be used. Also because in this way you cannot share the reactive power. You are not able to know. Let's assume your meters are perfect, but you don't know if the grid requires 100 megavars. You don't know if G1 will provide 100 and the second one 0, or G1 50 and G2 50, or 70 and 30 and so on. Exactly as happens for the frequency control. You know, Droop equal to 0 means that you don't know the sharing of the real power among generators. Okay? I assume you know how to manage these characteristics. I may make a lot of assumptions. The compound, sorry, this is the Droop. The Droop is the opposite of the compound. The Droop, if you remember, is this characteristic. Here I have the set point of the voltage. This is Droop equal to 0. This is Droop and this is the compound. Okay? So this means that as the loading increases, your set point is decreased. Should be completely useless. It's not so useless in this case, because here we saw that 0 is not possible. So when you have this scheme, what can you do? You can use the negative compound, that is the Droop. Because if you look at this scheme, you can measure the voltage here, but then as the load changes, you will not move on this characteristic because it's unstable, but you will move to this one, which is to compensate on the contrary. So behind you, you are measuring the voltage here, and you try to control the voltage in a point which is behind you. And in this case, you can check that the problem of instability is no more in place. So this works. Now coming back to the compound is typically adopted when you have this scheme. And you have the line here. So your meter is here, but you compensate the reactance of the transformer. If you compensate completely the reactance of the transformer, you will be in this situation. And if you do the same with this one, you are going back to this case. So you are trying to control by two generators the voltage at the common point of coupling with the network. And that's not possible because it's the same situation as here. So typically, the compound is a strategy to control the voltage by compensation of, let's say, 70% of the reactance of the transformer, which is here. So you can either use a regulator with a compound with compensation of 70%, or measuring the voltage here using a droop of 30%. It's the same. It's stable. It's insensitive to measurements error. Typically, in this case, you use the compound because it's cheaper than the droop in this case. So you can use all these, let's say, all these characteristics, but you must be careful because you need to look at the scheme of your power plant. So you must use the proper way to control voltage for every situation. I think that it's too late. Yeah. So I will leave you all the set of slides because there's a lot of other issues. If you can have a look, and if you need explanation even later, I don't know if there is the email. I can add the email address, or you can ask your professors. Okay. Any question? It's the typical unanswered question at the end. Okay. So thank you. See you tomorrow. Okay.